So Mr. Potter. In our previous video, we talked about the idea of a minimal spanning tree. In other words, how many branches can we get away with and still cover an entire network? Make sure every one of our servers and routers are covered so that a message can go from one place to another. And what that does is that minimizes the cost, but it doesn't necessarily minimize the travel time. So in today's lesson, we're going to be talking about the idea of a shortest path algorithm, finding the shortest path from some server to all of the possible destinations. We're going to be talking in particular about Dijkstra's shortest path algorithm because it's one of the ones that works very well. It's probably one of the most straightforward ones to analyze. So what I want to do first is I want to talk about the idea of a shortest path from something. And when I talk about shortest, I'm talking about shortest in terms of cost, because now instead of thinking of this as $2 million to lay network cable from A to B, think of this as you have server A, server B, and they have an agreement that every message that goes over this line, or every million messages, costs $2 million. And so you want to try and find the shortest in terms of cost path from A. So I'm looking at this. If I'm going to go from A to B, the shortest cost, the shortest path would be going along this $2 million path. It certainly is shorter than going this way from D and then to B. And it's a lot shorter than going from A to C to B, which would be $7 million. There's $5 million. This is just $2 million. Similarly, if I want to go from A to C, this $5 million path is actually more than if I was to just go from A to D, paying $3 million and then paying $1 million to go from D to C. So it certainly looks like this path here is actually shorter in terms of cost than this AC path. And then, of course, if I want to get from A to D, I could do $2 million, $2 million, so that's $4 million. This $3 million path is the best. And so it looks like this tree that I've diagrammed here is my shortest path from A to B, from A to C, following this path through D, and then finally from A to D as well. Keep in mind that if I was talking about the shortest path from point C, things are a little different. If I want to go from C to D, it's obvious that this $1 million path is the cheapest path. If I want to go from C to A, I could look at this $5 million path, I could look at this $1 million path and this $3 million path, or I could look at this $2 million path and this $2 million path. So I actually have two possible paths from C to A, one following the existing CD path up to A, and one following the CB to A path. So this is not the one that actually makes the determination from C, but I need to make the determination from other paths to make sure that other paths are included. So if I want to get from C to B, obviously going $2 million is cheaper than going $1 million and $2 million. So this is going to be part of the path. The question then is, which path do I need to include to make sure that I include A? And to be honest, I've got this $2 million path, I've got this $3 million path. The $2 million is cheaper than the $3 million, so this would be the best path to choose. But in reality, either of these paths would be fine. Either of these paths are going to have the cheapest cost in total to get from our source to any of the other nodes. So we're going to talk about this Dijkstra's algorithm. The idea behind Dijkstra's algorithm is we're going to figure out how much it costs from each vertex. So I'm going to talk about vertex A, and I want to get to vertex B, C, and D. And right now the cost to get from each of these paths, since we don't have a path, we go ahead and say that this is an infinite cost. So if I want to get from A to B is currently a $2 million path going through A. A to C is currently a $5 million path going through A. And A to D is currently a $3 million path going through A. So I've listed all of the possible paths, so what I want to do now is I want to identify which one of these is the cheapest. Right now, this is my cheapest path. And so choice B is actually going to determine where we go next. So I'm going to assume that we've made it to point B, but keep in mind that if we made it to point B, we've already incurred $2 million in costs. So any of our subsequent costs need to be cheaper than the costs we've already established for our path. So obviously, to get from B to itself, I'm not going to have to go anywhere, so I've already incurred the $2 million, so this is a $2 million path going from A. If I want to get from B to C is a $2 million path, but in order to get to B, I had to incur $2 million here. So this is actually a $4 million path going through B. Notice this is cheaper than the $5 million direct path we had from A to C. So this is actually a better deal, and we're going to record that. If I wanted to get from B to D, it would cost $2 million to go this path, plus the $2 million would be $4 million. But this $3 million path that we already have is the best deal. So this $3 million path from choice A is the best path. And I've already looked at choice A. So now what I need to do is look at what the next path is, and the next cheapest is this $3 million path from choice D. So I'm looking at choice D, but at choice D, at this point here, we've already incurred $3 million worth of cost. So if I want to get from choice D to choice B, I'm going to pay $2 million going this path backwards. But that would be on top of the $3 million that we already have, and that's $5 million, which is not less than the $2 million from the path going from A. If I want to get from D to C is going to travel along this path, which is $1 million plus this $3 million, but that's not less than the $4 million path that we already have from B. It happens to be equal, so it shouldn't replace an existing path that we have that already works. And then finally we have our choice D. To get to itself, it's not going to cost anything extra, but it's just this $3 million going from A. So I've already looked at this path here and this path here, so the last one I have is this path here, going to path C. Keep in mind, to go from path C, I've already incurred $4 million worth of cost, so I need to go, okay, how do I get from C to B? C to B would be along this path, which would be $2 million more, so that would be $6 million, so the $2 million path from choice A is still best. To get from C to itself, I'm just going along this $4 million path from choice B. And to get from C to D, I'm going this path, which would be a cost of $1 million on top of the $4 million, but the $3 million path from A is still best. So what I've done is I've actually gone through each of these nodes, and I've actually traversed each of these paths. And so my best deal is to get from A to B, I want to go directly. To get from A to C, here, this had to go through this $2 million path. And yes, there is a cheaper path that we could have done going from D through to C, but that wasn't cheaper, it was just the exact same cost, so we're not going to choose that path. And then if I want to get from choice A to choice D, I'm going to get this, and this tree that I've got outlined in blue, this is our shortest path from choice A. In other words, this minimized the cost of ascending of a signal from A to any other node on our network. So this is Dijkstra's algorithm. The idea is that I have to go through and check each of these. And at each of these, I'm going to take the best, and the best comes down to here. And I'm going to incur this cost of my best and try and revise. Notice that we had a little bit of revision here. Notice, however, that in the process of this revision, if I ever end up with something that's the same, like happened here, I stay with what I had before. And I need to make sure that I've actually addressed all the possible paths, making sure that I've gotten every single path visited and every single node visited. That's how I know that I've actually reached the shortest path. So a couple of things that we need to keep in mind when we're doing this is that we have to visit every node and every path. It's important that we hit every node, and it's important that we check every path, because it is entirely possible that the last path that we traversed ends up saving us more time or saving us more money. So the idea is that if I was to have a situation like this previous example, I had 4 nodes, I had 6 paths. So if I have 4 nodes and 6 paths, that really means that there are 10 things that I have to check. So notice what happened here is that I had my original set here, 1, 2, 3, and then I had to check modifications here and here because I had already assumed this was correct. And then I had to check modifications here, here, and here, and then I needed to check a final set of modifications here. So I'm always going to have that certain number of nodes and paths that I have to check as I'm going through this. But it's important that I check every node and every path because revisions could happen. So I want to do one more example of this. So I've got this slightly tougher problem. Again, A is going to be my source, but I want to make sure that I visit B, C, D, E, and F. And again, I'm assuming that because I haven't already established a path, that all of these costs are infinite. So I'm looking at A. Here is node A. And if I want to get from node A to anywhere else, I either have to go to node B, which has this cost of 8, or I have to go to node D, which has this cost of 7. So at this point, or excuse me, I could go to node C, which has a cost of 1. So I could go to B, which has a cost of 8 going through A. I could go to C, which has a cost of 1 going through A. And I could go to D, which has a cost of 7 going through A. But we still have no path to E and no path to F. We still haven't reached any of those nodes yet. None of those nodes are available through an edge originating at A. So I'm looking at these, and the cheapest one that I see, the best cost that I see, is this cost here, which means choice C, node C, is the next one that I want to investigate. And looking at node C, there are several paths that I could do. I could go back to A, or I could take this 6 to get to E, or I could take this 2 to get to F. So those are all the paths that I could do from C. So the thing is, from C to A is actually going to be, I've already know that that's my best deal right here. To get from C to B, there is no path from C to B. So because there is no path from C to B, I know that the 8 to A is still the best deal. I know from C to itself, I'm going to incur the cost of 1, but to itself, that's still going to be a cost of 1 originating from A. There is no path going from C to D, so for now, the best way to get to D is originating at A, which is a cost of 7. I can now get to E taking this path, which has a cost of 6. But if I add that to the 1, that means a cost of 7 passing through C is the best. And then I have a way to get from C to F that's going along this path that costs 2, but that's in addition to the 1 that we've already incurred, which means we have a total cost of 3 originating through C. Now, we've already analyzed this, so the next one that we need to look at, the next lowest cost, is actually this at node F. So I need to make sure that node F is the next node that I check, but I've already incurred a cost of 3 from F. Now from F, I can go from F to C, I can go from F to E, and I can go from F to D. I can't go from F to A. There is no direct line from F to A. So the path to A still has, from F to B, there is no direct path from F to B. So the best way to get from to B is still starting at A and taking the 8 cost path. If I want to go from F to C, I'm going to be going along this path here, but that's not cheaper than the 1, just our 3 in and of itself isn't cheaper, so 1 in A is the best cost. If I want to get from F to D, though, I'm going to be adding 4 to my existing cost of 3, but that's not better than the 7 we already have from A, so we're going to stick with that. If I want to get from F to E is going to cost 3 addition to the 3, which is 6, and 6 is better than the 7 cost we currently have from C. So we're going to say 6 from F is our best cost. And since we're at F, going to F doesn't cost us anything but the 3 we've already accumulated, so 3 from C is our best. Now at this point, we've already checked this and this node. Our next lowest node is going to be this F node. So I now want to check all of the paths from from E. So looking at E, which is this node here, E already has accumulated a cost of 6, and the only place I can go from E are to C and to F, paths that I've already done. So if I try and go from E to B, there is no path from E to B. So my best path is still the 8 cost from A. If I want to go from E to C, I'm going to be adding 6 to the cost of 6, which gives me 12, and that's no way that beats the 1 that we already have. If I want to get from E to D, there is no direct path from E to D, so that cost will stay the same at 7. If I want to get from E to itself, I can't do anything except the 6 that we've cost, but we've already got that 6 from F. And then we've got the 3 cost from F. If I want to get back to F, I'm going to add 3 to the 6, and that's going to give us 9. And that's not going to be better than the 3 we have to C. So at this point, I've already looked at the A, I've already looked at the C, I've already looked at this F. The next lowest that I have is what happened at D, which is a cost of 7. So I'm going to look at D, and D has a cost of 7. To get from D to B, there is no path from D to B. So because there's no path from D to B, that cost will remain 8. There is no path from D to C, so that's going to remain 1. There is no path from D to D. Well, D to D itself would just add an additional 7, which we've already got from A. D to F is going to add 4, but we've already got a 6, which is cheaper than the 7 plus 4. So we're going to stay the 6 from F. And then the 3 that we have from C, if I want to get from F to itself, that's only going to keep itself at 3. So now what I've done is I've analyzed this. I've got them all done. The 1, the 3, the 6, the 7. The only one I have left to look at is the 8. But looking at this 8, this is where B is, right here. There is only one path, and that's going back to A. So that's not going to change any of these. So if I'm looking at my best algorithm, I know that from A, the best way is to B. From A, the best way is to C. From A, the best way is to D. To get to E, the best way is to come from F. And to get to F, the best way is from C. And so I've got a path from A to B, from A to C. C also goes to F and to E, and A goes to D as well. So we've covered all of these possible paths. We found the smallest cost tree using Dijkstra's algorithm. So where we're headed with this is going to our studio.code.org website. So we're going to jump over there. There's some questions on here that you'll need to make sure that you address under the Stage 7 Algorithms Detour, the shortest path. So we're going to make sure that we cover these questions. So over here, you're going to have to find out which one of these is the shortest path. You're going to have to go ahead and answer a couple of other questions we've got here. Which of the following statements is false about minimum spanning trees and shortest path trees? Because there's a difference between what we did in our previous video and what we did today. Similarly, if we go on to question 4, it's going to say which of the following is not something we are concerned about when we write an algorithm. Question 5, if a graph has 10 nodes and 33 edges, how many nodes and edges will be visited as a result of running Dijkstra's algorithm? Give you a hint, all of them. And then analyzing algorithms, why doesn't the amount of real time tell us very much about the algorithm's efficiency? Notice that it took us a while. This is one of our longest videos for this class. But that doesn't mean the algorithm is a bad algorithm. My question is why? So, we talked about 2 different ways of looking at networks, one for minimizing the entire cost of the structure of the network, and one looking at minimizing the cost from a server to its clients. Both of these things are ideas that are considered when network infrastructure is being built and maintained, and both of these are going to be essential when we think about servers, routers, and clients on a network. So, once again, this is Mr. Potter. Thank you for watching. Have a great day.